All right, so here's another problem we're going to work on. We want to find the reactions again for this. Now, a couple of things that are a little bit different here. You'll notice first that the distributed load is different than we've looked at before. It's what we'll call a trapezoidal load, and I'll talk to you about how I like to handle those. We're going to assume here at A that that's a pin connection. It doesn't look like it. It looks like it might be fixed, but we're going to assume it's a pin. Also, a little word, a note that in the book and probably on the Mastering Engineering problems, if you see a drawing like this, read the description. It will tell you, assume A is a pin, assume B is a pin. It will tell you exactly what it is. Now, before we get started, I want to talk about something about what this BD element is. Does that look familiar to you guys? Well, first of all, one unique thing is there is no load. There's no applied load on that structure. Right? A, B, C, this beam, this horizontal beam, has a load applied to it. But is there an external load applied to BD? No. And the ends are pin connected. Does that ring a bell? It's called a two-force member. What does that mean, two-force member? That means there's only two forces on the member, and they pass through a line of action that connects the two endpoints. Basically, that's just an axial loaded element. Now, we'll talk about that more when we go back and review trusses and do truss analysis. By definition, trusses are composed of these kinds of elements. So there's not really two unknowns at D and two unknowns at B. There's only one unknown. We know the direction. It's along this line BD. I just don't know the magnitude. Okay? So let's start with that. So again, I'll draw my free body diagram of this thing. I may actually draw it a little bit bigger because it's kind of small here. So at A, I'm going to assume that I have a pin force in the Y direction up and a pin force in the X direction to the right. Then 6 meters over, when I get to this point B, I'm going to assume that B looks like this. I'm just going to call it force B. Since this is 60 degrees, I know this interior angle here is 30. So I'll also write here, that's 30 degrees. So I know the direction, I just don't know the magnitude. So how many unknowns do I have? 2 at the pin and only 1 at the bar. So this is 3 unknowns. So this free body should do it. Now how are we going to handle this trapezoidal load? Yeah, so what I like to do, and you've probably seen this before, is you can find the area of a trapezoid. That's pretty easy. But I don't remember off the top of my head where the centroid of a trapezoid is. So the easiest way I do it, and I'm sure you've done it too, is to break this up into a rectangular piece and a triangular piece. So let's look at the rectangular piece first. We know the area of a rectangle is base times height. The height of the rectangle is 2 kilonewtons per meter. The base is 9. So that's going to land right in the middle. 2 times 9 is 18. And then right in the middle, that would be, you split the 9 in half. So I'll just write over here that that's 4.5 meters from the left. And now, just to make it easier to see, maybe with color, I'll say this triangular piece is purple. What's the area of a triangle? 1/2 base times height. Yeah, so 1/2 base, 9. So what's the height here? The height of the triangle? Well, the total height is 4, but the rectangle height is 2, so the height of the triangle is just 2. So 1/2 base, 9, times height 2 is a force of 9. And then where's the centroid of a triangle? Yeah, so it's 2/3 the distance from the low end or 1/3 from the big end. So it'll land somewhere about here. And that's 9 kilonewtons. And 1/3 of 9 is 3. So I'll just use that to show the distance to here and the distance from there. Okay? One other thing I might want to do just to help you see it is already kind of help visualize the y and x components of B. So I'll draw those. Now, I'm not assuming those directions. Since I assumed B was in this direction, then vertical is down, horizontal is to the left. So I'm not making assumptions there. The only assumption I made in the direction of B was that it was moving down. That's everything I need. So now I can plow ahead. So how should I proceed? Should I sum forces in the x direction first? I can. Will I get anywhere? No, because I'll write one equation in two unknowns. Can I sum forces in the y direction first? I can, but again, not a good choice because I'd have ay and the y component of b. Two unknowns, one equation. So where's the best place to go? If I sum moments at A, I can write one equation and how many unknowns? 1, B. If I sum moments at B, how many? I write one equation and how many unknowns? 1. So either one would be a good place, but I like A. So I'm going to start there. So I'm going to sum moments about A. It kind of follows our general guideline in that it is a pin, and pins are always pretty good places to sum moments about. So looking at the applied loads, my 9 kilonewton and my 8 kilonewton about A, they're both going to create what kind of moment about A? I'm using the right-hand rule, so they're going to be both negative. So starting with the 9 kilonewton, it's going to be minus. So the force is 9 kilonewtons. And what's the distance from A to there? 3 meters. Everybody see that? Now from A, around A, the 18 kilonewton force, which is equivalent of the rectangle, also creates negative moment. Now I haven't done this one, but we can probably figure it out. I know the distance from A to here is how far? Half the total distance. Half the total distance is 9. Half of that is 4.5. So this should be 4.5. So that's the moment of the first force, the triangular force. There's the moment of the rectangular portion. So what am I left with? What's going on here? Does the x component create moment about A? No. But the y component does. So the y component is going to create what kind of moment? Positive or negative with my sign convention? Negative. And what is that component? It's going to be b times the sine or cosine of 30? Sine. Because here's the angle. The y component is opposite the angle. Sine is opposite. So I'm going to have minus b sine 30. That's my y component. And what's the distance from A to there? 6. One equation, one unknown. So what is B? It looks like B, the way I've drawn it, it's going to come out to be negative. Anybody know what's the value? 6 is
36.
36? Anybody else get 36?
Yeah.
So that'll be 36 kilonewtons. So that means B is negative. Do I rush over here and change the direction of B? No. I just leave it alone. Now I do know when I'm done and I want to interpret my results, I'll notice that this force is not in this direction. It's the opposite. But right now, leave it alone. So I need to find AX and AY. I could sum moments at B again if I wanted to, but some forces in X or some forces in Y are easier equations to do. So I'll start, really no reason, but I'll sum in the Y direction. So I've got AY acting up. Here's my BY. It's acting down. And BY is, so it's acting down, that's minus. And what is BY? It's B sine 30. What else is in the Y direction? 9 kilonewtons is down, 18 kilonewtons is down. So I have one equation in, looks like two unknowns, but I know B, so I can put it right in there. So my negative answer for 36 for B plugs in here, and that changes this to positive. So you don't have to worry about it. It'll take care of itself. So when I solve for AY, what do you get? 9. Anybody else get 9? You say yes, Mr. Jafari? So that's 9 positive?
Yes, sir.
Excellent. And then last, we'll tidy it up by summing forces in the X direction. And I'll assume to the right is positive. So AX is to the right, so that's positive. What else is in the X direction? Well, not the applied forces, but there is an X component of B. And what direction is it in? Negative. So that's going to be minus. And what is the X component of B? Well, it's going to be B cosine 30, right? And then you can plug B in. The negative and the negative cancel. Make a positive, right? So what is AX?
Negative
31.2. That sounds reasonable. Anybody else get that? So that'd be negative 31.2, and that'll be kilonewtons. Now, if you're asked, and you should pay attention on Mastering Engineering because it tells you what direction. So even though you might assume this in your work, when you go to report your answers, it's going to say assume positive is to the right, or positive is up, or creates this kind of moment. So make sure you keep an eye on that. If you want to come back onto your free body diagram and straighten things out, well, then now's the time to do it. So I can redraw the diagram, and now I can put values on it. So AY was 9 kilonewtons up, positive, so I have a reaction force here of 9 kilonewtons. AX is minus 31.2. I assume to the right, so it's actually to the left. B is negative 36. I assume down, it's actually up. And then, of course, just to finish it off, we would still have the same concentrated equivalent forces if you wanted to represent those. And it kind of makes sense. You can see these guys are all pushing down, trying to make the structure rotate clockwise. So BY pushes up counterclockwise. Since BY is pushing up, B is pushing up and slightly to the right, that's why your reaction has to pull back to the left. And depending on the magnitude of these, this could have been negative if these forces had moved out a little farther, but it's okay. That's correct. I'm not going to ask you to do this in your work, but just be aware that that would be the kind of the final solution down here in the corner. So any questions about that one?